This is called connecting f, f prime, and f double prime. The handout that you have that has all this is one of the most important handouts in calculus. It says when f prime is positive, f is increasing. When f prime is negative, f is decreasing. When f prime is 0, f is flat or horizontal. If f prime does not exist, that's where f has a sharp turn, like possibly this. I've got a better example. Sharp turn. If the second derivative is positive, f is called concave up, like this over here. If the second derivative is negative, f is concave down. The phrase concave up means any tangent line will be below the curve. These green tangent lines are below the blue curve. Concave down means any tangent line will be above the curve. This green tangent line is above the blue curve. Any tangent line is above the curve when it's concave down. On page 204, exercise 8, y equals negative 2x to the third plus 6x squared minus 3. There's a lot of questions to answer. We'll read the questions after we find the derivative. Label it y prime. Negative 6x squared plus 12x. Find when the derivative is equal to 0. 6x can be factored out of negative x plus 2. 6x equals 0 when x equals 0. Negative x plus 2 equals 0 when x equals 2. So now we're going to make a chart with y, which represents that. Y prime represents that. And the x-axis. On the x-axis, locate these critical values. These are called critical values. 0 is called a critical value because when x is 0, y prime is 0. 2 is a critical value because when x is 2, y prime is 2. So all of these labels, very important. Y prime is 0 when x is 0 or 2. Plug a number before 0 into y prime. You can plug into here or over here. We're plugging in negative 1. Negative 1 is positive 1 plus 2 is a positive times a negative, because where the x's we're plugging in negative 1, and 6 is positive. Multiply these three things, we get a negative. Plug in any number in this interval, 0 to 2, so plug in 1. Negative 1 plus 2 is positive. This will be positive, and 6 is positive. 3 positives multiplied gives us a positive. Plug in a number over here, 3 for instance. Negative 3 plus 2 is a negative number. A negative times a positive is a negative. This tells me that y is decreasing. When y prime is negative, y is decreasing. When y prime is positive, y is increasing. When y prime is negative, y is decreasing. And now we're ready to answer the questions that are in the textbook. Part A says find the intervals on which the function is increasing. I just look here. I see the interval where the function is increasing is 0 to 2. These are both x values, the x interval from 0 to 2. Part B, find the intervals on which the function is decreasing. There's two of those, decreasing here, here meaning from negative infinity up to 0, from when x is negative infinity up to when x is 0, round, square. Also decreasing over here, decreasing, going down from 2 to infinity. Square bracket, round. Part C and D we can't answer yet. We'll get back to those. Part E, find any local extreme values. That means local maximum. That would be here. If we have going up and then going down, we call this maximum. The x-coordinate is 2. The y-coordinate is found using this right here. This says what y equals. When x is 2, y comes out to be 5. Just plug 2 in there and you'll see that. Y, plug 2 in here. Y comes out to be 5. And we're still on part E. Local minimum. You can tell over here, this is their minimum is right here because going down then up. So right here is minimum when x is 0. When x is 0, plug 0 into what y equals. Y is negative 3. So these are points, x and y, x and y. Over here, these are intervals. From x equals 0 to x equals 2, that's the interval where the function is increasing. And part F, we're not ready to answer. So we're now going to find y double prime, the second derivative. The derivative is over here. The second derivative is negative 12x plus 12. The second derivative is 0 when x is 1. We're going to make a chart similar to this one, but instead of y prime x, it's y double prime x. And this time the only important number is 1. When x is 1, y double prime is 0. Important labels. Stick a number that's smaller than 1 into y double prime. So if you choose 0, negative 12 times 0 plus 12 is a positive number. Stick a number more than 1, like 2, into y double prime. Negative 12 times 2 plus 12 is a negative number. This tells that y is concave up. When the second derivative is positive, y is concave up. CUP is short for concave up. When y double prime is negative, y is concave down. CDN, concave down. Second derivative negative, y is concave down. Back in the questions, part C, find the intervals on which the function is concave up. That's from negative infinity to 1. And these all get round parentheses, no squares. Concave down, CDN, concave down is here. That's from 1 to infinity. And part F, so we have parts A, B, C, and D are all answered. Part F says find any inflection points. An inflection point is a point where a graph changes concavity. If there's a change from concave up to concave down, or vice versa, concave down to concave up, we have an inflection point. So because there's changing concavity here. The x-coordinate where it changes is 1. The y is found by plugging 1 in here. Over here in the purple, that's what y equals. Plug in 1. When x is 1, 2 times 1 cubed plus 6 times 1 squared minus 3, that's 1 also. So there's the inflection point, 1, 1. All of this was done without a calculator. We just had some arithmetic to do to get the y values. We also did some arithmetic to get the signs, the pluses and the minus. Easy arithmetic. All of these results can be seen on a graph. It did not say to graph this, but if you look at a graph, you'll see all of the things we just found. The local maximum, the local minimum, 2, 5, 0, negative 3. I think that's what we wrote. Also, inflection point 1, 1. So local maximum means where the graph changes, where the function changes from increasing to decreasing. Local minimum means where the function changes from decreasing to increasing. Inflection, point of inflection, means where there's a change in concavity. If I trace this graph all the way up to its point of inflection, I would say to you, all of that green is concave up, because any tangent line you draw, if you draw a tangent line on this green, anywhere on the green, it will be below, the tangent line will be below the green. For example, right here, that purple is below the green. The rest of the graph, I'll make it red, from the point 1, 1, and after that, the rest of this is called concave down, meaning any tangent line on the red part will be above the curve. Here's a for instance. This purple is above the red. We're going to do one more example. Number 28. Y equals x over x squared plus 1. All the same directions as the last, parts A through F. The derivative of this is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So it's x squared plus 1 times 1 minus 2x squared all over x squared plus 1 squared, which is combining like terms 1 minus x squared all over x squared plus 1 squared, because x squared minus 2x squared is negative 1x squared. This derivative is equal to 0 when x is 1 or negative 1. If we put negative 1 or 1 in here, square and then subtract 1, we'll get 0 over something. So the derivative is 0 when x is plus or minus 1. When we make this chart, y prime, and x, we locate the critical values. X values that make the derivative 0 are called critical values. In this case, negative 1 and 1. I'm indicating the reason these are critical values. Y prime is 0 when x is negative 1 or when x is 1. Also, whenever you do a problem like this, you need to know when the derivative does not exist. Not existing would be when the denominator is 0. In this case, this denominator is never 0, except if x is an imaginary number, the number I. But we don't use imaginary numbers because they wouldn't be, there's no place for an imaginary number on this line. So, but consider that, think about when is the derivative non-existent, because you would have to put those numbers here also. But in this case, the derivative always exists. If you pick a number smaller than -1 and plug it into y prime, which is up here, say you plug in -2, do the arithmetic, you'll get a negative. Plug in any number between -1 and 1, like 0. Use any number you want. You can use a half if you want. Whatever number you plug in between -1 and 1 makes y prime positive. And then plug a number over here, like 2. Plug in 2 into the derivative. 1 minus 4 is a negative number. This denominator is always positive, by the way. If you square anything, it comes up positive. Y prime negative means y is decreasing. Y prime positive, y is increasing. Y prime negative, y is decreasing. So part A. Find the intervals on which the function is increasing. That's here, -1 to 1. Square. Part B. Find the intervals on which the function is decreasing. There's 2 of those. Here, -∞ up to -1. Remember, these are x values, left to right. Round, square. Also here, the x values here are 1 to infinity. Square, round. Part C, can't answer yet. Part D, can't answer it yet. Part E, local extreme values. Local max is when x is 1. When x is 1, use this to find what y equals. Y comes out to be a half. Local min, minimum, it's over here. Down then up, so minimum when x is -1. Plug -1 in up here. This is what y equals. When x is -1, y comes out to be -1/2. And part F we can't answer yet. So the second derivative, the derivative is up here. Put a purple star there. The derivative of the derivative, that's called the second derivative, is the denominator. That's x squared plus 1 squared times the derivative of the numerator minus the numerator. Now for the derivative of the denominator, I need more space. So I'm going to write it smaller. The denominator times the derivative of the numerator minus the numerator. The derivative of the, so I didn't have enough room here. The derivative of the denominator is 2 times 1 times x squared plus 1 to the first power, the exponent becomes a 1, times the derivative of what's in the parentheses. So let's just check it out. So far I have the denominator by the purple star times the derivative of the numerator minus the numerator times the derivative of the denominator. That's the power rule. 2x squared plus 1 to the first power times the derivative of what's in the parentheses. And all over the denominator squared. X squared plus 1 squared squared. So the second derivative is a mess. I'm going to write this. -2x times j to the second minus 4x times k times j all over x squared plus 1, actually all over j to the 4th. So the trick I'm using here is everywhere I saw x squared plus 1, I'm putting j temporarily. There's a j, there's a j, and down here that's j to the 4th. And everywhere I saw 1 minus x squared, which was only one spot, I put a k in that spot. Also, this negative 2x, I put that in the front. Also, this 2 times 2x is 4x, I put that in the front. There's a k and a j. If I do this, it makes it easy for me to simplify, because then I can see that both of these are negative, so I'm going to factor out a negative. Both of these are even numbers, 2 and 4, so factor out a 2. Both of these have x, so I'm going to factor out an x. And they both have j to the first power. When all of that is factored out, what's left here is j minus 2k. So just double check. Make sure negative 2xj times j is negative 2xj squared. So I'm double checking and realizing that should be a positive, because negative 2xj times positive 2k should be negative 4xkj, and it is. Now it's very easy to see that this j and one of these j's cancel. So it's negative 2x times j plus 2k over j to the 3rd. Can't think of anything else to do here, so I'm going to turn j back into x squared plus 1. And 2 times k, right there, 2 times k, means 2 times this. Right here, this is k. All over j to the 3rd, that would mean x squared plus 1 to the 3rd. So the second derivative is negative 2x times x squared plus 1 plus 2 minus 2x squared. I'm just distributing the 2 over x squared plus 1 cubed. After distributing this 2, that's all I did, I see like terms. The second derivative equals negative 2x times 3 minus x squared all over x squared plus 1 cubed. 1 plus 2 is 3. X squared minus 2x squared is negative 1x squared. So we need to know when the derivative is 0 and when the derivative does not exist. This derivative always exists because x squared plus 1 is always positive. It's never 0. The denominator is never 0. But the numerator is 0. The numerator of this fraction is 0 when x is 0, or when x is plus or minus the square root of 3. Just solving these. So now we're going to write y double prime, and x, and we have 3 numbers to look at. We have 0, we have the square root of 3, and we have negative square root of 3. All of these numbers make y prime 0. You pick a number smaller than negative radical 3 and plug it into y prime, wherever that is. It's up here somewhere. You could pick any number smaller than negative radical 3. You could use negative 10 if you want. You're going to plug it into y double prime, this thing. And I'm thinking plugging in negative 10. you get a positive, I'm pretty sure. I'll double check this. Pick a number in this interval, negative radical 3 to 0. I believe negative 1 is in this interval. You plug in negative 1. Be sure you get a negative in y double prime. Number in this interval, which is 0 to radical 3. So positive 1 you could use. I think you get a negative again. I'm pretty sure. I'm going to double check these though. Plug a number bigger than the square root of 3, like 10. It's going to be a negative times a negative. I think you get positive there. Alright, so, okay. I want to check these again. Let's use negative 10. Negative 10 squared is 100, but 3 minus that is going to be a negative. And that's negative because I'm plugging in a negative. And that negative 2 is negative. 3 negatives makes a negative. So that should have been a negative there. Because this denominator is always positive. You square whatever you're plugging in and add 1, it comes up positive. So this is going to be changed. That's a negative. Number between here, and here is negative 1. Negative 1 squared is 1. 3 minus that is positive. We're plugging in negative 1, so that's negative. Negative 2 is negative. The denominator is always positive. 2 negatives and a positive, so that's correct now. Plug in a number between 0 and radical 3 like 1. 3 minus 1 is positive. I'm plugging in 1, so that's positive. Negative 2 is negative. 2 positives and a negative make a negative, so that one's correct. And if you plug in a number more than the square root of 3, like 10, this thing in the parentheses will be negative. This x will be positive because we're plugging in 10. The negative 2 is negative. 2 negatives and a positive make a positive, so that one's right. So when y double prime is negative, y is concave down. When y double prime is positive, y is concave up. So back to the questions. Part C said, on what intervals is the function concave up? And we're coming up with from negative radical 3 to 0, and also from the square root of 3 to infinity. Part D, concave down intervals. That was negative infinity up to negative radical 3. And also from the interval from 0 to the square root of 3. So concave up from negative radical 3 to 0. Also from radical 3 to infinity. Concave down from negative infinity up to negative radical 3. Also concave down between 0 and radical 3. And then the last part of the problem was to find the inflection points, INF, inflection points. That's where concavity changes. So we have concavity changing at this x value, negative radical 3, concavity changing at x equals 0, concavity changing at radical 3. So these are the x coordinates of the points of inflection. The x coordinates are negative radical 3, 0, and radical 3. The y coordinates, you have to find them by putting these x's into what y equals in the beginning. And you can do that and see that you'll get, when x is radical 3, y comes out to be radical 3 over 4. When x is 0, y comes out to be 0. And when x is radical 3, y comes out to be radical 3 over 4. So those are the inflection points. And you can see all of those on this graph. Two of the inflection points I forgot to label on here, but there's one inflection point because there's a change from concave up to concave down. And maximum is where there's a change from increasing to decreasing. The change from red to green is called inflection. Minimum is where there's a change from going down to going up, decreasing to increasing. And the other two inflection points are over here somewhere, because there is a change in this graph from concave down. Somewhere along the way it changes back to concave up. Same in this direction. This red thing is concave up, but it does change somewhere to concave down. Concave up is where the tangent lines are below. Concave down is where the tangent lines are above.